Right, hello and welcome. This is question 5 for Edexcel M1 January 2003. Now, this is probably the hardest question that I've seen. Definitely the hardest question on this paper. I think it's probably just because I'm a bit of a simpleton, but whatever. I personally think it's quite a difficult question. So as you can see, we've got an inclined plane there. However, this one is a little bit different to the ones we generally see. We've got a block, obviously, standard. It's got a mass, we're told, of 1.5 kilograms. It's been pulled with T newtons, which are an angle to the slope, 20 degrees. So we're going to need to solve the vertical and the horizontal components of that. Also, we've got a totally different force pulling it up, called F equals UR. And we've got a force pulling it down the slope, parallel, but the slope both ways, mg sine theta. We've got a weight, mg, we've got mg cos theta going into the perpendicular to the slope. Okay? Right, so we're given the coefficient of friction is a third, and we'll get to that end bit in a minute. Right, so the first thing, because we're told this is just about to start being pulled up the slope by this T newtons, because remember when we were saying when we didn't have this T newtons, we just had F equals UR, then it couldn't be possibly being pulled up the slope, because the whole idea of that is resistance forces, and you can't have a resistance force going in the direction it's moving. But now we've got this T newtons because we've got essentially got two forces here. We've got the frictional force, they're going up this way, and we've also got this tension is pulling it up, this unknown force, which we've been asked to find out. Okay, so the angle of the slope is 30 degrees, and the angle between the T newtons and the slope is 20 degrees. Right, so okay, so what do we need to do? Well, we need to calculate forces perpendicular and parallel to the slope. Now, I said this T newton has got perpendicular, so it's got horizontal, so basically it's going parallel to the slope and it's going perpendicular to the slope. Perpendicular, I call that the horizontal component of T, and parallel to the slope, I call that the horizontal component of T. Okay, so what does this mean? Right, well, if we work out the parallel part first, and the reason we're doing all this, and not just doing, because you may be asking, oh, well, why aren't we just doing mg sine theta minus UR and working out from there? Well, because we've got two forces here you have to contend with, so we can't use that one. The idea we're going to use that, we are, but not into that easy extent. Okay, so it's parallel is the first one that I'm going to talk about. So, because we know this is in equilibrium, and it's just about to move, this means it's all equal to 0. So any more pulling it up, any more tension up this way, it'll start to move. Okay, so parallel forces. What forces have we got acting on this block that are parallel to the slope? Well, we've got mg sine theta, that's the kickoff. So I'm just going to write all the forces down, not in any order, but I'm just going to write them down. So we've got mg sine theta, we've got F equals UR, or you just write UR. I'm just going to write UR. So we've got mg sine theta pulling it this way, UR pulling it that way, and we've also got T newtons. However, this T newtons, to resolve it parallel to the slope, we have to times it by cos 20. Okay, so I'm going to leave it as that. Now, here comes the tricky part. You would naturally assume, would you not, that we're going to start with mg sine theta. We're going to say mg sine theta, take T newtons, take F equals UR, or maybe something like mg sine theta, take T newtons times cos 20, and then in the same brackets, UR. Okay? However, we're not, because we're told this is almost being pulled up the slope, so T newtons is almost getting bigger. This is the way I think of it. So therefore we put T newtons first. So Tn times cos 30, no, cos 20, sorry, because, yeah, 20, because we're considering the small angle there, take mg sine theta. Now I'm going to write the proper values for these in a minute. Take mg sine theta, take UR, equals 0, remember. Okay, so we're going to call that equation 1. Now, obviously, you know what u is. Third, you could stick it in there if you want to. However, to work out what r is, we're going to have to, we can't just do mg cos theta as being r like we normally do if we weren't being pulled at an angle. But because we're being pulled at an angle, we have to consider this vertical force pulling it upwards as well. So therefore, this vertical force, because if it's pulling it upwards of this component of t, and it's greater than mg cos theta, which is pulling it down into the slope, then it'll be taken off. So therefore, this horizontal component of t must be equal to mg cos theta. In other words, the perpendicular, because these are the only two forces that are acting perpendicular on this block, so the ones that are acting perpendicular are the horizontal component of t and the vertical thing pulling it into the slope of mg cos theta. Now, it doesn't, this one it mattered which way you were taking it round. Well, you put where, but for this it doesn't matter because your mg cos theta is the same size as your horizontal component of t newtons, which is obviously going to be Tn, or t newtons, sorry. This Tn bit, instead of just calling it t newtons, you could just call it t. This t times sine, because we're doing with the opposites, and hypotenuse, sine 20, sorry. So, it doesn't matter which way you put it, I'm going to put it Tn first. So t newtons times sine 20, because we're dealing with opposites, and hypotenuse, obviously, sine 20 and not 30 because we're dealing with a little angle at the top. Take mg cos theta, and we're told we know that is equal to 0. We're going to call that equation 2. Okay. Right. Now this is equal to the horizontal, the vertical, the perpendicular force. So we're going to call that r. That's what r is. So equation 2 equals r. So you can take r is Tn sine 20, take mg cos theta. This mg cos theta being theta of 30 degrees, sorry. Because we're considering a slope. Whereas in that, we were considering the perpendicular factor of t. So we had to include that 20. But when we were talking about the force pulling it into the slope, that has nothing to do with t. So we use the angle of the slope. Okay? So we've got two equations there. Right? So what we're going to do, because this equals r, and we've got r in the first equation, we're just going to sub this equation into r there, because that equals r. So why not? Let's have a go at this. My pens are going to work. So therefore, we don't know what t newtons is, so we're just going to use t newtons times cos 20. Take mg sine theta, which we'll put this in brackets, 1.5 kilograms, or just 1.5 times 9.8 times sine 30. Okay. That is take. Sorry, I can't really fit it in here. U, which is a third, brackets r, and then just copy this in, which is t newtons times sine 20. Take mg cos theta, which is 1.5 times 9.8 times cos 20. Cos 30, sorry. Okay. And remember, that still equals 0. So all we've done for this part is subbed this equation into that r there. So if we simplify this down, so by simplifying down, what I just mean is getting all your t's together and eliminating it really. Okay, so what we've got is we've got t, obviously t newtons, t times cos 20. Well, the first thing I'm actually going to do is simplify this down. Yep. Sorry, one sec. And so that's plus a third t sine 20, because we're just grouping the t's together. So the third t newtons times sine 20. Take 1.5 g. Now they've in the answers they've wrote 9.8 as g. So, but I'm just gonna simplify it down. So we'll need to calculate what 1.5 times 9.8 times sine 30 is. 1.5 times 9.8 times sine 30, which is the fraction of, so this is take, by the way, 147 over 20, or 7.35. Because this 7.35 comes from that, so that is 7.35. This 1.5 times 9.8 times cos 30 is 12.7, but you need to, because this is times by a third, you need to times 12.7 by 1 over 3 or third. And that gets you take 4.24. Okay, so if you were to simplify them down, so 7.35 take that, you get t times cos 20 plus a third of t times sine 20 take, oh sorry, I made a bit of a mess of that. You get minus 11.59 to 2 decimal places, and that is equal to 0. So what you do, simplify this down. So you bring the 11.59 over to the right hand side. So t times cos 20 plus a third t times sine 20 equals 11.59. Okay, so then when you've got to this stage, just a case of simplifying it down. So you could group it. So what one thing you could. Anyway, I'm just gonna assume you can do it actually, because I'll probably, if I do it now, I'll make a mess of it. So that leads us to say t is equal to 11 newtons. Sorry about not doing that last bit. I'm just I might add it on, but I mean the main bit was getting that. If you got all that, then that's brilliant, because I mean I'm still not 100% because it's quite weird for me. Okay, so if you think you can explain this parallel bit why we've put Tn cos 20 first, I mean I tried to stab at it, but if you want to put it on the comment section for other people, just to try and gauge a response, because I don't think I've explained it terribly well. I mean obviously I didn't get it, but hopefully you do, because I've tried to explain it the best I can. But limits, integration, that's all. Didn't work that, but you know what I mean. So anyway, that's how we'd work that out. The key thing from this really, I mean if you got that, if you put mg sine theta first, which is probably what in the exam I probably would have ended up doing that, so don't feel too bad if that's what you naturally do, because I naturally put mg sine theta first, and work from there, but have the same method, but obviously get a different value for t. They're not going to penalise you twice. You only lose a mark for putting mg sine theta first, but the rest of your working should be fine. So as long as you did that, that's the main thing really. Another common mistake as well, obviously looking on the marks, you can probably tell, but obviously because we've got two angles here, people will start putting angles in the wrong place. Now remember, when you resolve in t in terms of the perpendicular vector, the perpendicular part of t, or what I call the vertical bit, you always, or you calculating the horizontal bit of t, or the parallel part of t to the slope, you always use 20 degrees in this question, because you always use the angle that's associated with t. This angle isn't associated with t, because this angle could be 1,000, well, not 1,000, actually it couldn't be, you know what I mean? 1,000 take 963. There you go. That's good enough. And t would still be 20. Well, it might not be, but you get the idea. This could be anything, but you wouldn't change your answers for t here, because you're still going to use cos 20 or sine 20, whichever is relevant. Perpendicular. Now, the reason why we said this and we didn't just say, I mean, in realistic terms, you would say mg cos theta take mg cos theta, because r is obviously 0 and this perpendicular one is always 0, but we put t times Tn times sine 20 because that's what's actually pulling it up. Because naturally there'd be nothing pulling it up apart from if this wasn't here, the vertical part T, then you just have the natural force of the floor pushing it up, and that'd be equal to mg cos theta anyway. But we just have to include this T sine theta. Okay? So hopefully that explained it. Just one more thing I want to add into that actually. This T newtons and this F equals UR business, they may be, especially when you resolve T newtons in the parallel sense, so when we did, Tn times cos 20, that is not FR, F equals UR. And that is because this T newtons is a totally different thing. So if we think of it, if it wasn't being pulled by T newtons, I mean obviously it'd start moving, but say if it wasn't for some reason, this F equals UR business, that would still be there. So therefore it obviously isn't part of this T newtons bit. So when you resolve it, it doesn't include F equals UR in that answer. Because as I said, this is a totally different force, and that's what's actually keeping it in the equilibrium position. That 11 newtons that we worked out. Right? So I think that's explained everything now. Because I've just worked through the answers, and then because I don't want to start explaining this and then lose track of where I was, because you can see at the end there I got into a bit of a pickle. So as I said, that is definitely the hardest question I've ever seen, and I don't suppose the next question is going to get any easier. Double check. No, it doesn't. It's nice and hard work. So anyway, that's question 5. This is quite a nasty paper actually. So a few nice questions at the start, but I think that is. I mean, you are doing further maths. Obviously, this is not physics. You can tell AS physics is a hell of a lot easier than this because you just do mg sine theta. You don't even have any resistance forces to worry about. So you doing AS physics definitely help with this. Understanding the cos theta and sine theta bit, but beyond that, this is purely just now M1. Okay, so thanks for watching. If you have any ideas, if you have a better way of explaining it, and an idea of a better way of explaining why we put Tn cos 20 first, I would more than welcome that. Because I don't think my explanation is very good. I mean, I might upload this question again, which is pointless me saying that because this won't be on there. Or there might be 2 question 5s. That'll be why, if there is. So anyway, thanks for watching, and we'll see you in the next video, which will be a nice hard one.